In the previous unit, you learned about the groups of the periodic table, how different elements on the periodic table sometimes have similar properties based on their electron structure, and they're grouped together on the periodic table based on those similar properties. That's one of the things that makes the periodic table so useful. But remember, it's not just that every element can be grouped according to similar properties. Every element has a unique atomic structure as well that gives every element a certain unique flair. It gives it differences from other elements. And in this unit, we're going to be looking at how you can use individual element squares on the periodic table to learn something about the way individual types of atoms are structured. So while the previous unit was more about sameness, this lesson is going to start a unit that's more about the uniqueness of every element on the periodic table. And what we're going to learn to do in this lesson is read the periodic table of elements. How can you look at those individual unique elements in each square of the periodic table and understand something about how they're structured? That's what we're going to start learning about in this lesson. To start that, we're going to consider some of the numbers and letters that are on each element square to help us understand what each element square tells us. First off, a very important number that's pretty much on any periodic table you look at is the atomic number. It's the number at the top of the element square, and it tells you something very important. That atomic number tells you the number of protons in that atom. Remember, protons are what give an atom its identity, so that number has to be different for each different type of atom. Boron has 5 protons, or another way to think about it, any atom with 5 protons has to be an atom of boron because those protons give it its identity. The atomic number is very important. Other things that are important, though, include the element's symbol and the element's name. Now, the element symbol and element name are very important when you are representing elements in chemical formulas. When you are working with elements, it's very helpful to know how we name them and how we represent them with symbols. One important thing to know is that all elements either have a 1-letter or 2-letter symbol given on the periodic table. If the element symbol is just 1 letter, that letter is capitalized, like the big capital B in boron. If the element symbol is 2 letters, the first letter is capitalized and the second letter is lowercase. The reason we do that is when you write out chemical formulas and chemical equations, you need to be able to keep track of the individual elements in those formulas, and you can do that easily if it's first letter capital, second letter lowercase. The element name is pretty straightforward. These are the names that we use to refer to all of the atoms that make up everything in the universe that God created. However, there is one thing that's not so straightforward with the element name all the time, and that is there are a bunch of element names that just don't match the element symbol. For example, silver is Ag, gold is Au, potassium is K. Where did these strange symbols come from, and why don't they match the name? Well, the reason for these symbols is that they're given after the Latin name of the element. However, instead of naming the element after its Latin name, we chose to use a more common name for what we refer to these elements as. So silver in Latin is argentum. But nobody really uses the word argentum anymore to refer to silver, so we just call it silver, but we use the old Ag symbol for it. And this list shows you all of the elements' names that don't match up with their atomic symbol, most of them because the symbol is in Latin and the name is the more common name we use for that element now. So now that you understand the most basic information on the periodic table, let's take a look at one of the numbers on the periodic table that's not so simple, and that is the average atomic mass, which is usually located at the bottom of the element squares on the periodic table. Now, this number is a little confusing. You might remember that atoms are made up of protons, neutrons, and electrons. Protons have a mass of 1, neutrons have a mass of 1, and electrons have a mass that's basically 0. It's so small that it's negligible. So if this is the atomic mass, the mass of an atom, and both pieces that I can add together to make atoms have a mass of 1, how in the world can I have a mass that has a decimal in it? How can it be 10.8 instead of either just 10 or just 11? Well, it all comes from that first word, average. I'm going to show you where the average atomic mass comes from by looking at the element boron. Boron has to have 5 protons in its nucleus to be boron. So here I'm going to start building a boron atom. And in order to do that, I have to start with 5 protons. Same with this other atom of boron that I'm going to build. So I've got 2 atoms of boron started, and they're boron because they have 5 protons in their nucleus. However, to this first atom, I am going to add 6 neutrons. It's still boron because it has 5 protons in its nucleus, but it has 6 neutrons for a total mass of 11. 5 protons plus 6 neutrons, each with a mass of 1. When I add those all together, it equals 11, a total mass of 11. This is what most boron found in nature is like. 80% of the boron found in nature has 6 neutrons along with its 5 protons. However, 20% of boron found in nature has 5 protons still, but just 5 neutrons. Because 5 protons plus 5 neutrons, each with a mass of 1, has a mass of 10 total, we call this boron 10. Now, to complete these boron atoms, we also have to give them electrons, but remember, the electron mass is negligible. It's so small it doesn't even count. So how do we get that number 10.8? Well, if 80% of boron is boron 11 and 20% is boron 10, the average mass of a boron atom in nature, the average mass of the isotopes is 10.81. So can an atom of boron be in between? Can it have like 5 protons and 5.8 neutrons? No. There is no such thing as a part of a neutron or a part of a proton. That doesn't happen. But what does happen for most atoms is in nature there are several different isotopes of those atoms, and when you take the average mass of all of the isotopes, you get a decimal number, and that's the number that's on the periodic table. To use that number, you have to round it off to a whole number, and that will usually give you the most common isotope of that atom that's found in nature. Now, it's important to note that both of these boron atoms are exactly the same. They have the same appearance, the same properties. The only difference is that boron 11, the more common isotope, is just a little more massive than boron 10. All right, and then finally, on the periodic table, sometimes there are some extra numbers that are extra helpful for us. Other information on periodic tables might include, but not always, maybe you'll find the boiling and melting point of that element. Maybe you'll find the density of that element in nature. And then you also may see numbers that show possible ions that that element might form. So atoms of boron might form 1+ or 2+ ions, but because the 3 is in bold, most of the time they form 3+ ions. This is the information that you can find about each individual type of atom on the periodic table. And hopefully now you understand that the periodic table gives a lot of information that's useful about individual atoms, but also from the previous unit, the periodic table also tells you trends and patterns that helps you understand similarities between those individual atoms as well.